Ever wondered how your favorite apps or websites keep your data safe while still letting you ask questions? Like, how do they stop a query from accidentally revealing your medical records or a CEO's salary? Today, we're diving into a smart solution called Controlled Query Evaluation, or CQE for short. It's like having a digital bouncer that lets the right info through while keeping secrets locked up, even when the system is packed with rules. Let's start with the basics. Imagine a database as a giant, organized library where every book data is connected through logical relationships. This is called an ontology, a smart filing system that knows how facts link together. But here's the problem. Sometimes these connections can accidentally expose secrets. For example, if someone asks, who earns more than $100K? The system might infer a manager's salary from other facts, even if that number isn't explicitly stored. Ouch, privacy leak. That's where epistemic dependencies, EDs, come in. Think of them as the database's privacy rules. They're like a company's policy. Salaries are confidential unless you're a manager. EDs translate these policies into logic, so the system knows exactly what to block. It's like teaching the database to say, nope, can't show that rules are rules. But how do you actually enforce these rules? Enter censors, the digital gatekeepers. They're sets of facts the system can safely share without breaking the rules. The trick: making sure these censors are maximal. They reveal as much as possible while still keeping secrets. For example, if a manager's salary is allowed, the system must hide their subordinates' salaries, even if they're in the same database. It's a delicate balance between openness and protection. Now let's talk about the tough stuff, complex queries. Imagine asking, are there any managers with salaries over $150K and consensual relationships with employees? These are called Boolean unions of conjunctive queries, BUCQs, and they're tricky. The research team cracked this by rewriting these queries into simpler forms using first-order logic, a math-like language that's super fast to compute. This means the system can check if a query is safe without slowing down, even with huge datasets. The proof of the pudding. They tested it with real-world scenarios using a benchmark called AltaBench. The results? Their method worked efficiently, like a security guard who's both strict and super quick. No delays, no leaks. So why does this matter? In fields like healthcare or finance, where data privacy is critical, this tech could prevent disasters. It's not just about hiding info. It's about enabling smart systems to work without compromising confidentiality. Now, let's zoom in on the mechanics. At the heart of this system are binary epistemic dependencies, simple, two-part rules like, if someone is a student, they can't be a professor. These rules are deceptively powerful because they work seamlessly with a logical framework called DL-Lite R, which is optimized for handling massive datasets at lightning speed. Translating these rules into DL-Lite R syntax is key. For example, that student-professor rule becomes a format the system can process. This means we can use existing tools to validate the rules. No need to start from scratch. But here's the catch. Not all rules are created equal. Researchers tested acyclic policies, no loops, and binary policies. Most queries ran in seconds, but one complex query took minutes. This highlights a critical challenge, balancing expressiveness with efficiency. What's the takeaway? Binary EDs are a game changer. They're efficient, easy to implement, and could revolutionize data systems. But we're not done yet. Future work will tackle more complex rules and expand these ideas to other domains. Thanks for watching. If you're curious about how logic shapes the digital world, hit subscribe. And drop a comment. What's one rule you wish computers could follow? Let's keep the conversation going. Stay curious and see you next time.